Good afternoon, friends. Welcome to the lecture of real analysis as an introductory lecture number 4. In the last lecture, we have seen the concepts regarding sequences. What is a sequence? What is convergence of sequence? What is the bound of a sequence? Okay, this part we have see. Now in today's lecture, we learn this concept of well-definedness, why the function we are proving to be well-defined, and why the way we are using to prove the function to be well-defined. Anyone from the student side? Have you seen this? Okay, I will give you today's time also to just check out what is the meaning of function to be well-defined. Let me continue with this lecture of knowing what is function. Function definition we have seen in the last lecture. Let me go directly for writing the limit of a function. Limit of a function. Yes, from the students, anyone want to tell me the definition limit of a function? If f is a function we are defining, suppose from A to B, A is the domain, B is the codomain. Then when we are going to say that the limit of the function exists, what are the types of limits you have studied? Or here one can define from R to R, real valued function. From R to R. When we say that the limit of a function exists. Yes. There are two types of limit actually. Okay. First is left limit and right limit. Second is right limit. Second is right limit. Okay, whenever we are considering a limit of a function at a point A on a real line, we know that there are two approaches, two ways to come towards the point A. One approach is from the right, you can come towards A. Okay, so for whatever the points we have on the right of A, we have to make something minus so that we can come towards A. Similarly, we can come from the left side. Therefore, on the real line, there are two ways to approach towards the point A. The first way we are calling from the right, from the second way we are calling from the left. Okay, therefore there are two types of limits are going to exist. Correct? Suppose we want to define the limit of a function here at point A. At point A. Okay. Now what is the limit of a point? Limit of a function at point A? When we are saying the limit exists, at the knowing you are knowing both the left and right limits, I will write directly. Okay, function f is said to have limit. Said to have limit L say at point A E. What if for epsilon greater than 0 there exists delta greater than 0 such that what such that mod of f of x minus L less than epsilon whenever mod of x minus a less than delta. Instead of writing whenever, we can write this in other words. That is, mod of x minus a less than delta implies mod of fx minus L, mod of fx minus L less than epsilon. Less than epsilon.
मैम आवाज येत नाहीये.
आवाज येत नाहीये. Everything is fine from my side actually. Now check. Is it audible now?
Yes, ma'am.
Okay. Shall I continue? When we say that the limit of the function exists. Okay. Now let us come to a next definition of continuous function. When we say that the function is continuous, continuous function. Yes, when we say that the function is continuous, a function or a real valued function is said to be continuous is said to be continuous at point x is equal to a e. For every epsilon greater than 0, there exists delta greater than 0 such that, what such that? Mod of f of x minus f of a less than epsilon whenever mod of x minus a less than delta. Okay, again in other words we can write the definition. Mod of x minus a less than delta implies mod of fx minus f of a less than epsilon. Okay, therefore if you compare the definitions of limit of a function and continuous function, the definition goes parallelly. Instead of the limit L, if the limit value of the function is f of x, the function is continuous. In other words, if I want to explain the definition, this is what a textbook definition we have. Let us try to understand the definition of this modulus function. What it is implying us, that whenever definition of this modulus function, what it is implying us, that minus delta strictly less than mod of x minus a strictly less than plus delta. Okay, what in turn it implies to us, that this is, yes, a minus delta strictly less than x less than a plus delta. The concepts goes parallel to this point also. For me I write f of x, or here I can write minus epsilon less than f of x minus f of a less than plus epsilon. Therefore adding f of a throughout, one can write this is f of a minus epsilon less than f of x less than f of a plus epsilon. Therefore, what this statement is giving us? This statement is giving us a clear idea that whenever an arbitrary point is in the open interval a minus delta to a plus delta, and if it will imply that the corresponding f image will lie in the open interval f of a minus epsilon to f of a plus epsilon, then continuity at the point A holds. Then continuity at the point A holds. Let me tell you with a simple sketch how this is going to hold. Okay, suppose this is the point A, and this is okay. Similarly, if we have f of x to be a real valued function again, then one can show this f values on the real line. F values on the real line. Suppose somewhere here is our value f of a, then what is this interval is suggesting us this is the epsilon neighborhood around f of a. Therefore, we have to mark the 2 points on the left and right of f of a with epsilon as a distance. Therefore, this will be f of a plus epsilon, and this will be f of a minus epsilon. Correct now? Therefore, the definition of continuity says whenever an arbitrary point x in this neighborhood, in this open interval is there, then it will imply the corresponding f image. Correct now? See, I just mark it with a different color pen so that you will get a correct idea. Right? This is an arbitrary point. If it is in this neighborhood a minus delta to a plus delta, then if its f image, that is f of x, if it is going to fail under this neighborhood f of a minus epsilon to f of a plus epsilon, f of a minus epsilon to f of a plus epsilon, suppose this is the point A and this is the delta neighborhood around A. This is delta a minus delta to a plus delta. Suppose somewhere here is my f of a value and here be the epsilon neighborhood, f of a minus epsilon to f of a plus epsilon. Let me just draw those horizontal line to understand where is the location for those points. Correct now? Okay. Now let me mark these points with some different color pen again. Vertical lines. Okay. Now what we are saying, whenever our x fail in this interval, say x I am writing, then its corresponding f of x value should be in this interval. Okay, then for every epsilon, that however epsilon we may make small or we may make large, such a delta is going to exist. See what I am saying? For every epsilon greater than 0, there exists delta greater than 0. There exists delta greater than 0. That however we can make epsilon smaller or however we can make epsilon larger, this delta value is going to exist. Then and then only one can say that the function is continuous. This is called as the geometric aspect behind the function. Okay. Now let us try to understand with one more way. We are checking whether the point is continuous. Okay. This is the a value suppose, and this is the f of a value of the given function, and somewhere may be the nature of this function curve. Let this be a curve, correct? We don't know what is the nature of curve. We want to just check out whether at this point the function is continuous or not. Okay. Now whenever we say that x tends to a from the right or from the left, then this f of x must tends to f of a. Correct? Now we know that alternative definition for the limit continuous function. What is the alternative definition? We know limit x tends to a, f of x is equal to f of a. This is the limit definition. You can see both the meaning of both the definitions is similar. But whenever x is reaching towards a from the right or from the left, f of x must reach towards a. Okay, and the value, limiting value must be equal to f of a. And whenever such a point exists, we can plot the point of the given. We can plot the point on the given plane. In that case, one can say that the function is continuous. Here you can check from the left and from the right. The limiting value of the function f of x is equal to f of a. Correct? Any difficulty toward this limit function? Yes, students? Are you understanding this fact or not?
Yes, ma'am.
Can anyone tell me the example then? Example of a continuous function? Do you know any example of a continuous function? So that we can find out a delta for every epsilon. Okay, because we want to find out the condition. We want to check out the condition. Whether constant function is continuous or x belongs to real numbers. Whether this function is continuous?
Yes, ma'am.
Yes, it is continuous. Okay. How this going to be represented on a 2D plane? Suppose somewhere here is my value c, then f of x equals to c means what? This will be a horizontal line. Na? For every value of x in R, the value of f of x is c. Therefore, this is the graph of the constant function. Now let us check. Let me take any point, say A. Let me draw an epsilon neighborhood around the point. Then here is f of a, na? That is c. Therefore, if I make some smaller epsilon around this point, C minus epsilon to C plus epsilon, then whether the delta I can find out very easily. We'll go according to the definition. What definition says that whenever mod of x minus a less than delta, it will imply mod of f of a minus f of a less than epsilon. Can anyone tell me epsilon delta relation in this example? Yes. Can anyone tell me epsilon delta relation? काय आहे इथे epsilon delta? What? Because here the value of delta depends on epsilon, no? Yes, students. Can you tell me the epsilon delta relation in this example?
Delta depends upon the chosen value of epsilon.
Good. But what is the exact relation in this example? Can you tell me for which value of epsilon what will be the delta? Can anyone? Have you done the examples before like this? Finding delta for the given epsilon. I think we have taken this example, no? In convergence of a sequence. I have shown you with one example that how for every epsilon there exists a stage in sequence conversion. Likewise, for every epsilon, delta exists in this case. No? Can anyone tell me the relation? How this is going to exist? From students side, I want answers. You should try to speak, though your answers may go wrong, but try to give the answers. Because these are the points which are making your basic clear. So that you can explain these examples in future. Hmm. Mod of x minus a less than delta implies f of x minus f of a less than epsilon is the statement, and we want to find out the epsilon delta relation. Can anyone tell me how can I find the epsilon delta relation? Hmm. What is f of x is in this case? It's a constant function, na? Hmm. Okay, you just think on this how one can find out the relation between the epsilon delta value. Let us go for the next example. Suppose I am writing f of x is equals to x for x in R again. Whether this function is continuous, what kind of representation it will be, what kind of graph it will be. How can I draw a graph of the function f of x is equal to x on a R2 plane? Yes. What kind of graph it is? If you want to know more about the functions and their graph, there was a nice book called as Play with the Graph. It is available in our department library as well. Okay, you just take that book and read so that you can have a clear idea how the function is going to behave in a two-dimensional plane or in a 3D space. Because unless the graph of the function is in front of our eyes, it was somewhat difficult for us to judge about those examples. Correct, na? One should know the graph of this function. F of x is equals to x is actually a straight line. It is a linear function. Therefore, it is a straight line bisecting the first quadrant. F of x is equal to x. From this given sketch, can anyone tell me whether the function f is continuous or not? By looking at the graph of the function, is it possible for us to understand whether it is continuous or not continuous? Can we have the idea of continuity? सांगता येऊ शकतो का आपल्याला ग्राफ बघून?
Yes, ma'am. It is continuous.
continuous. But this is not always a criteria to understand the continuity of the given function. Correct? Therefore, if or is it possible for us that not continuous curve will give us a continuous function? That is, if I define the same example f of x is equal to x, but instead of defining it is on R, if I define it on the set of natural numbers, what kind of function it will be? And we want to check whether it is continuous on n or on z plus or on z, anything I can define. Correct. What kind of curve, what kind of graph it will take then? What kind of graph it will take then? F of x is x for all x in z or z plus or in n, anything you can consider. Correct now? This is x axis, this is y axis. We are saying f of x is equals to n. X for x is equal to n. For n I will draw 1, 2, 3, 4 and 5 and continue. These are the points of your domain. Correct? Then for every domain point, what is the corresponding f image? For f of x is equal to, for x is equal to 1, what is f of x? 1 itself. Na? For here also I have to mark the points 1, 2, 3, 4 and so on. Next point is x is equal to 2. For x is equal to 2, f of 2 will be 2. Therefore, this is the second point, correspondingly third point, fourth point. Okay, but here all the points between 1 to 2 are not the points of our domain of the function. Are not the points of the domain of the function. Therefore, we cannot consider the points in between. The points of the domain are simply 1, then 2, then 3, then 4 and 5. Okay, therefore, between the points 1 and 2, we are not going to consider. Therefore, here if we look at this, this will be the graph of the function. This locus of points will represent the graph of the function. Now, one has to check the continuity of this function. Okay, therefore, instead of taking this example, one can explain in general also what the function, what the definition of a function is saying us of continuity. Whenever we have a delta neighbor around a point A, then whenever a point X is in this neighborhood, it must fail under this neighborhood. F of A minus epsilon 2, f of A plus epsilon. Let us check. If I consider 1 as this point, this is 1 say, 1 is the point. Then 1 is the only point which fails under the delta neighborhood. Which fails under the delta taking very small, fails under only one point. Then this point must going to lie, what is the f image of that corresponding point? F of 1. I'm going to lie a equal to 1 is the point we are considering. Right now, if a is equals to 1, what is this point? F of 1 minus epsilon and f of 1 plus epsilon. And obviously, f of 1 is going to lie in this neighborhood. F of 1 is going to lie in this neighborhood. Therefore, one can write very easily. Whenever 1 belongs to 1 minus delta to 1 plus delta, it will imply f of 1 belongs to f of 1 minus epsilon to f of 1 plus epsilon. Therefore, according to the condition, or according to the definition of continuous function, the function is continuous at a is equal to 1. Correct. Let us do the same thing for a equal to 2. Whenever we take a is equal to 2, 2 will lie in the interval 2 minus delta to 2 plus delta, and as it is the only point of the domain, its f image f of 2 must lie in f of 2 minus epsilon to f of 2 plus epsilon. Therefore, in general, there is only one point x in the neighborhood a minus delta to a plus delta, where the corresponding f of x lies in f of a minus epsilon to f of a plus epsilon, and according to the definition of continuous function, this function is continuous. This function is continuous. Though we are not having a continuous curve as a graph of the given function, but still the function is continuous. Therefore, one can say, one can make a very easy statement Whenever a function is defined on the set of integers, on set of positive integers, or on the natural numbers, the function is always continuous. Without knowing the nature of the function, one can guess this. Correct now? I don't know how many of you are getting me. If you have a difficulty, you can ask. Therefore, the conclusion we have made from this definition that all the functions defined on the integers are the continuous function, though it do not have a continuous curve. Though it do not have a continuous curve. Is this point clear to everyone? Okay, functions having continuous curve are no doubt going to be continuous, but functions having not continuous curves also, because continuous curves is the concept possible only if you are considering the domain to be the real numbers or subset of real numbers. Okay, instead of subset of real numbers, I will say intervals, open or closed intervals, then only it is possible. But for the other subsets of the real numbers, this is not always possible for us to get the continuous curves. Okay, can anyone tell me the nature of the function f of x equal to x square, and is it continuous on x in R? Simple examples I am considering so that your concept will get clear. Yes, is this function continuous? How is the graph of the function? Can anyone tell me? I request everyone to just use the book Play with Graph. In that book, it was very clearly given function, its graph in two-dimensional plane, in three-dimensional space. Okay? Yes? Can anyone tell me the graph of this function?
Parabola in first and second quadrant.
Good. The parabola. Touching origin or not?
Yes, ma'am. Touching origin.
What is the shape? U shape?
U shape. Yes, ma'am.
Is the function continuous?
Yes, ma'am.
Yes. Now for every example, you have to tell me epsilon and delta relation. This is your today's homework. Everyone please note this. Okay. Next example, if I take f of x equal to mod x, say. Let me just make the interval to be -1 to +1, or closed -1 to +1. What is the nature of this function? Mod x, modulus function. What is modulus function? How can I represent it on the graph? Can anyone answer? How this mod x is going to be defined? Mod x is x for x greater equal to 0 and minus x for x less than 0. Correct, na? So that it will in turn gives us the non-negative values. Okay, the graph of this function is of this type, V shape. Okay, and this is a continuous function. Again, I want epsilon and delta relation in this function. Okay, likewise you may go for many more definitions. I'll just switch to a next definition of uniform continuity. I'll just shift to a next definition of uniform continuity. Okay, a function f defined from R to R is said to be uniformly continuous if for every epsilon greater than 0 there exists delta greater than 0 such that, what such that? Mod of fx minus fy less than epsilon whenever mod of x minus y less than delta. Again, in other words, we can write the definition, or whenever mod of x minus y less than delta, it will imply mod of f of x minus f of y less than epsilon. Again, one can say that whenever the distance between the two arbitrary points is getting smaller and smaller, less than delta, na? Then the distance between the corresponding f images should be less than epsilon. Correct now? This is what the idea is actually. Whenever I have 2 points x and y on the x-axis, and whenever the distance is less than delta, that it is becoming, the points are coming closer and closer, then the corresponding f images, f of x and f of y, should, the difference should be less than epsilon. That is, these 2 points should come closer and closer, and whenever this situation holds, we can say that the function is uniformly continuous. Can anyone tell me the example of a continuous function? Sorry, uniform continuous function. Any example of uniform continuous function? Whether f of x equal to x is uniformly continuous? Have you studied this definition or not? Uniform continuity. Have you studied this definition in your graduation level? Hmm? I hope you have studied all these definitions. You have to just recall those concepts. Okay. Now, f of x equal to x, you have to check whether continuous or not. You have to check for f of x equal to x square. You have to check for f of x is equal to 1 by x. Okay. You have to check for f of x is equal to a constant function as well. A constant function as well. Okay, this is what for today's lecture, continuity and uniform continuity. Okay, I have tried to explain this by the sketches also. Okay, for every example, you should, for every concept, you should try to check the aspect geometrically so that the concept will be very clear. Okay, now what is the today's homework? Whatever the examples of continuous functions we have checked out, you have to tell me epsilon delta relation in the every example. Similarly, you have to check the uniform continuity of these 4 functions. I want the answer in the next lecture. Okay. Now I think this is sufficient as an introduction to real analysis. From the next lecture, I am going to start the actual syllabus of Riemann integration. Okay. Integration is known to you, everyone. What is integration? Inverse of differentiation, right now? Okay. Therefore, for tomorrow's lecture, you have to prepare these points. You have to tell me what is the definition of integration and how this integration gives us the, or what it gives us geometrically. Okay. Because once we understand what the integration gives us geometrically, we will try to understand how the origin of integration starts, how the formula is being built up, etc. And those everything was given by the mathematician Riemann. Therefore, in next lecture, we are going to understand what is Riemann integration. We will start our first unit of Riemann integration in the next lecture. Thank you for watching today's lecture. If you have any difficulties, if you have any queries, you can ask me. Please unmute yourself and you can ask. Thank you for watching the lecture.